Hello. This lecture is about a case study I conducted at a large retailer doing the exact things we covered in the first lecture within this module, which is supply chain optimization for an intermodal network. So when I think about the logistics network of this retailer, they have a variety of suppliers that through less than truckload trucking deliver goods to consolidation facilities, consolidation points, that are subsequently, through either full truckload or a combination of truckload and rail, sent to distribution centers for subsequent distribution within their own network to their stores. Now, some suppliers could ship direct from the suppliers to the distribution centers, bypassing these consolidation points. They could do that through either less than truckload, which are the short 28-foot trailers like you see on the road, often in tandems and in pairs. Some UPS will drive those, for example. Or the full truckload trailers, which are the 53-foot trailers that companies like J.B. Hunt, Swift, Schneider, etc. will drive. And we have this idea that these suppliers, through different modes of transportation, are trying to get their goods into the distribution centers so that the retailer can put them into their stores so people can buy them. Now, if we have some number of suppliers, some number of these facilities, and some number of distribution centers, this problem could be just an academic exercise where we're simply looking at onesies and twosies. But in the real world, as you realize, it's a little bit at a bigger scale than that. It's a little bit more complex. We have these consolidation facilities, as I mentioned in the last lecture, because you don't want every supplier shipping to every single distribution center. These suppliers can't afford that transportation costs. So if they can have, instead of one item going to one distribution center and two items going to a different distribution center from the same supplier, they'll put three of them on the same truck, send them to the consolidation facility, and at that location, they'll get broken apart into a truck to the one and a truck to the two. So we're looking at total logistics network cost minimization here with multiple modes of transportation. I'm going to kind of walk you through in this lecture the process we went through to build the optimization model. And the next lecture will actually show you some of the experimentation and results from our optimization-based study. So if you look at the locations in the continental United States of all of their consolidation points, they are where the population lives. I mean, you see some out in California, but the majority of them are in the Midwest and the East Coast. Our goal here was to analyze their distribution network, their supply chain, at different levels of utilization, at different levels of traffic or busyness, to figure out what's the right way to route goods from suppliers to consolidation points to distribution centers. We also looked at a simulation study after we did the strategic optimization to optimize or improve upon the performance within a triangle. In other words, at a given consolidation point, when I have goods coming in the gate, I want them to be taken apart, sorted, put on the rack, put in outbound trucks, and out my door in 48 hours was the client's stated turnaround time. So while our strategic study is looking at the relationships of suppliers, consolidation points, and distribution centers, the phase 2 of the project was a simulation study on the facility logistics level using much more operational decision making, looking at time periods of hours rather than, as you'll see here for the optimization study, a 5-year period. So this two-phase approach, as I mentioned, the optimization is a static deterministic problem, looking at long-term network configuration and growth, and the simulation study was within one specific consolidation point, looking at the dynamics, the cycle times, the forklift driver's work schedule, the real fine details, with probabilistic travel times and probabilistic demand arrival rates, figuring out how feasible can we get things through these center points based on the quantities and the loads that our optimization model prescribed to us to do. So let's talk about the optimization study first. So here, over a 5-year time period, the client wanted us to look at, which of the consolidation points should be expanded based on demand requirements, which of them, if any, could be closed based on cost considerations, And should we open or build any new ones in any location based on how we see the demand patterns evolving and where basically it's all full in our network and we need more capacity. Again, we're looking at cost minimization across this entire network. Now, this is a 5-year strategic study. And looking at 5 years in terms of time buckets, we were instructed by the client to aggregate into 6-month time buckets, if you will. So if we're doing 2 periods per year, because a 6-month time bucket gives us 2 6-month time buckets per year, over a 5-year study, this is a 10-period strategic optimization model. And when you're thinking about expanding interacting facilities and the way that we route or distribute from suppliers to consolidation points to distribution centers, this is something that the company typically looks at on a 6-month basis. It's not something they're going to redesign every Monday. So the fact that we are mimicking their typical decision horizon in our model was an important point that we had to make sure we did to gain credibility with our efforts. So, how do we go after this problem? Well, we're minimizing cost. We had to look at transportation cost in terms of the trucks, which are both less than truckload and full truckload, as well as the intermodal costs if we did a combination of rail with truck travel. We have constraints. Well, this is the client's network. They have demand at the distribution centers, which is being created by items being consumed in their stores. So as people buy things at their stores, they're replenished from the distribution centers. Well, that means the distribution center is maintaining inventory. And as its inventory gets consumed or depleted, it has demand to get additional inventory supply from its suppliers. So we have to meet all of the demand. In other words, the distribution centers need the goods that we state their demand is. We can't short them. We have different transportation vehicles, the trains and the trucks, that have weight, capacity limitations. They can only hold so much poundage. And they have cubic or volume considerations. They can only hold so much material. Think about hauling a truckload of Gatorade versus a truckload of tissue paper. Well, you're going to cube out a truck with tissue paper before you hit its weight limit. Similarly, if you haul Gatorade, pallets of Gatorade are pretty heavy. Soda, fill in your beverage of choice here. You're going to weight out the truck before you cube it out. So a lot of the advanced practices people do typically is they put heavy stuff on the bottom and light stuff on the top so they can weight and cube the truck out. So for example, the Gatorade rides at the bottom and they pack the top with tissue paper to fill the entire box of the truck. Finally, the consolidation point capacities were given to us in terms of how many pounds or how much cubic volume per dock door at these facilities is it capable of processing per day, per hour. We can scale it up to the appropriate unit of time. So that if you think about these consolidation points, they're very large warehouses, often 500,000 to 1 million square foot, with a number of doors where trucks back up, unload their goods, and leave, and other doors where trucks back up, get loaded, and leave. Well, each of these dock doors has workers and other resources associated with it, and they have some rate at which they can unload a truck. Therefore, we got from the client how much pounds we could expect each door at this facility to do. Similarly, how much cube do we expect it to do? Finally, for each consolidation point, we know how many number of dock doors there are, and we learn from the client whether each one of them could be expanded or not. If there was available real estate, if it was not their building, if they were leasing it, they weren't allowed to expand it. So all of these are important factors and constraints as we start to go after our modeling project. So for this consolidation points, we had to get the name of them, their current location, number of dock doors, the capacity in terms of pounds per dock door per week. Remember, we're doing 6-month time horizons, so we need that to kind of roll up 26 weeks of capacity. Which distribution centers the consolidation points could actually currently have relationships with getting freight to it. The distances of each consolidation point to all of the different suppliers, because if we're looking at cost minimization, and transportation cost is a key to us, transportation cost is often a surrogate for the miles that we drive, where we have a rate per mile, or we have some fixed amount based on what we have Shorter distances, it may be a fixed trip charge. Longer distances, it may be rate per mile. Also, we need to know the cost by the different modes of transportation. So all of these inputs had to be gathered and collected in order to build our optimization model for this strategic 5-year study. Finally, distances to the distribution centers. We also have to know that the relationships of all of the nodes and the arcs within our supply chain network. I guess not finally. And the cost of shipping to the DCs by the different modes of transportation. So we have shipping from the suppliers to the consolidation points, the different modes and costs and capacities, and relationships of how it's connected. And then from the consolidation points to the distribution centers, we have all of the same information that we have to collect. So, what type of demand information do we have to gather? Well, for each DC, we need to figure out how much it wants from each supplier for every type of product it stores in terms of weight in pounds and volume in cubic feet on a 6-month basis over a 5-year time horizon. Well, that seems kind of like a daunting task, so I'm going to kind of walk you through how we came up with those estimates. So we had to say, we're not going to assume our suppliers can't make what we demand. We're going to assume unlimited supply. If we wish to be very detailed, we're going to be realistic in our demand assumptions because we're going to show you we base it on what's actually occurring. So we know they can supply it. We don't want to have our suppliers constrain our solution. We're going to assume that being a large retailer, if we tell the suppliers we need more, they're going to get it for us. We have our demand that I mentioned both in pounds and in cubic feet. And we have as many cars and trains as available to us. With all the third-party logistics providers, if I need more trucks to move goods, they'll be available to haul my stuff. And I could say, though, for a given lane between any 2 nodes in the supply chain, I can tell you what modes of transportation are available to me, whether it's only truck, whether it's intermodal. And as I mentioned, we talk with the client, and we have a per mile cost for distances that were greater than 150 miles. If the trip was less than 150 miles, there was a fixed rate. So we have the different costs that are available in our model so that we could trade them off. So as we started to develop the model, we developed it in Ample. Now Ample is a front-end modeling package where you put the logic of the model, you put the objective, you put the variables, you put the constraints. No data of the problem. I kind of represent the fact that I have suppliers, I have consolidation points, I have distribution centers, I have modes of transportation. But I'm not telling it specifically which ones I have, because those would go in what's called the data file. This way, one model can be used to analyze hundreds or thousands of different data files, different scenarios, seamlessly, so that you build the model very compactly, and it expands automatically based on the data that you give it. Whether you're looking at a supply chain with one supplier, one consolidation point, and one distribution center, or as you'll see here in a minute, something just a little bit bigger. We use CPLEX to analyze this model. CPLEX is one of many different commercially available optimization solvers. It actually connects or talks to Ample, takes our model and the data, builds it together, and then analyzes this large-scale optimization model. I'll call this here an industrial strength optimization solver. There are others that are available too. One of the benefits of being an academic is that we get all of this software for free, so we can use it, we can test it, we can use what we like. When we work with clients, if they wish to actually incorporate these models, well then they're going to have to buy the software themselves. Just like in your 855 class, how we can use Arena for free. If a company wishes to procure Arena, it's going to cost you something. I think that's one of their hooks, to get academics to know their packages, to teach to our students, and then when they go to work, hopefully they realize they need that package and they'll buy it for their company. So here's an example of an Ample model, kind of an eye test, right? This is just a flat text file. The model here gives me all of the consolidation points, the distribution centers, suppliers. And notice I'm not telling you how many there are. I'm just simply saying I have them. I have different parameters like, and this is a comment marker, so it's kind of explaining to you the distance from supplier to the consolidation points in miles. I have a variety of parameters involved in this model, and these parameters are indexed over the relationship of, if I have a distance between a consolidation facility and a distribution center, that exists for every combination of CP to DC. So if I have 5 of one and 10 of the other, there are 50 of these values. So very quickly, the scale of these models can grow when you realize you have all of these different indexes or subscripts that you have to have the data for. So if I have the dock door, this is the number of dock doors at the consolidation facility in each time period. Remember, the time periods were the 6-month time buckets over a 5-year period. Well, initially I can just say I have time periods because this model is generic. If I give it the 6-month time periods over 5 years, fine. If I give it just 2 years, fine, it can handle it. That's why we like to separate the modeling from the actual instance data or the experiment we're wishing to run. There is much more to this model, but the one thing I wanted to show you here, if you look at my primary decision variable, so we call it for some reason X. X is indexed by supplier, consolidation facility, distribution center, mode of transportation, and time period. I define this as the fraction of demand shipped from supplier I through consolidation facility J to distribution center K by transportation mode M in time period T. So there are 5 different dimensions to my X variable. So if I have so many suppliers, so many CPs, so many distribution centers, so many modes of transportation, and so many time periods, how would you figure out the number of X variables in my model? Well, you'd actually multiply all of those terms together, such that if I just had, to make it easy for you, 10 suppliers, 10 center points, 10 distribution centers, let's say 1 mode of transportation, and 10 time periods. That's 10 times 10 times 10 times 1 times 10. That's 10,000 different X variables that this optimization model is going to have to figure out or prescribe to us the values of. The problem is, in real-world studies, there's not just 10. So these models, as I mentioned before, are not solved in Solver because these things just get out of hand really quick. But the nice idea here is that we have the model and the logic separated from the data. We can have the model test it on a very small test case, make sure it's working, validate it, and then we can scale it up by just getting larger and larger data files. So how do we validate our model? Well, we built a little test case with 3 center points, 3 consolidation points, 6 distribution centers, and 10 suppliers. Well, if I look at that, that's 3 times 6 times 10. That's only 180 combinations. Not so bad. We can do that. All suppliers were capable of shipping to all consolidation points and all distribution centers. So we fully connected the network, right? We looked at some simple data. We compared it in Excel. We looked at what the optimization model was telling us. We manually looked at the solutions. And we got, as expected, the right demand was satisfied, the costs were calculated properly, other parameters, everything looked good. Because we didn't want to throw the whole entire network at this thing not knowing if our model was correct. We had to start with a small, what we call a toy problem, or a test case, and validate that all of our modeling worked. All of the optimization modeling with the constraints and the objectives and the costs and the distances, everything was getting picked up properly. So with that, we were confident things were looking good here. So let's expand the model a little bit, right? So we started adding some constraints about weight and volume limits on our trucks, because either of these things can restrict the capacity, because we're trying to figure out how many trucks we're going to need. So if I have a weight limit and I'm trying to ship in excess of the weight limit, I need an extra truck or 2. If it's a cube limit, I need an extra truck or 2. Either of these can cause us to require more trucks, which require higher transportation costs. So when the model's deciding what to source from what location by what mode of transportation, these are important considerations to make sure we properly tabulate all of the costs and get the best cost optimal solution. Because the model is calculating how many trucks, both at full truckload, less than truckload. Clearly, since it's a 28-foot trailer versus a 53-foot trailer, we have different weight and cube capacities, as well as how many rail cars that we needed based on what they can haul. So this is the size of the monster here. we are looking at 19 consolidation points, 40 distribution centers, and over 2,000 suppliers. So this is a little bit bigger than 10, 10, 10, right? So if you did this math, it's about 20 times 40, which is 800, times, let's just call it 2,000. Well, that's 16 with 5 zeros. So that's 1.6 million variables before we even talk about 10 time periods. Okay, 16 million variables. 3 modes of transportation. Okay, 48 million variables. Now, not every CP can connect to every DC. Not every supplier can connect to every CP. So it's a lot smaller than this 48 million. But the combinatorics, this combinations here, this is a field called combinatorial optimization. All of these different combinations really make things blow up very quickly that render solver completely useless. So if you look at this model here, you say, okay, you said you've got this great model file, just put these in the data file and let it go, right? Well, problem is we couldn't handle it. The model was too big for our computers. Even if we only took from the 2,000 suppliers, we took the top 100 suppliers from all DCs. We ran the model for a day because, you know, this is a strategic study. We don't have to have this answer in 2 minutes. Let's give it 24 hours. In 24 hours, our model was still no closer than 40% away in terms of the best solution. So 40% gap, 40% difference between the model's current solution and its best estimate of what it could be is really not acceptable because 40% is a lot of wiggle room, right? So this approach was not working for us. We expanded it, we couldn't handle it. The model was incapable of being solved. But this isn't a theoretical study here that I just want to write up and publish a paper on. This was for a real client who wanted real answers. So what are you going to do about that? Well, we did something else. It kind of made sense after the fact. We didn't come up with it at the first point, but when we realized if we aggregate the continental United States by 3-digit zip codes, and what I mean by that is the first 3 digits of the zip code. So here I'm in 29631, my house. Clemson's at 29634. Well, in the 3-digit zip, they're both 296, so they get aggregated together, such that as we roll these up across the U.S., we actually ended up with 19 center points, 40 distribution centers, and 412 3-digit zip codes. So you may say, well, that's not that much of a difference. Well, actually, yeah, it helps out a lot because instead of 2,000 times 19 times 40, it's a fifth of it. And by aggregating this 3-digit zip, we can have as many suppliers as you want because the 3-digit zips aren't going to change. If I have 10,000 suppliers, if it's still within the same geographical area, they will just roll into one of the existing 412 3-digit zip codes. I would say the opportunity to expand the 3-digit zip codes is there, but it's not going to happen that often, such that our model size would remain consistent and stable over time. So this is one of those aha moments where once we figured out the 3-digit zip roll-up, it was kind of obvious, but before that, we were looking at individual suppliers. So now we just have to translate where the suppliers are located, regardless of how many there are, and get them into the right 3-digit zip code because that is sort of our pool for our suppliers now. It's not individual suppliers, it's geographically the 3-digit zip codes around the country. So, what did that do for us? Well, it helped tighten the model, make it smaller, helped us to solve it more easily. So we went from 354,000 variables in our model. Remember I told you there was 48 million, but that's if everything was connected everywhere. But we were able to cut that by more than half, down to 172,000 variables. We had 84,000 constraints. We were able to get that down to 35,000 constraints. Now, hopefully, this is impressive to you. 172,000 variables. Dun-dun. Well, these real problems have a lot of variables in them, and these commercial solvers can handle them. I mean, when we talk about large-scale optimization, this is what we're talking about. This isn't onesies and twosies. But in order to do this, we were able to drive that 40% gap after 24 hours to within 0.5% of optimal in 30 minutes. So this is kind of a big deal, because now in 30 minutes, I can get you to within 0.5% of the true lowest cost solution, rather than waiting 24 hours to find out that I was 40% away. So the client was pretty happy here. They said, wow, Mason, you and your team have done some good work here, right? Well, we were pretty pleased with it, because through industrial engineering techniques and how we model the data and some of the art and the science put together, we actually were to create a large-scale supply chain optimization model that was tractable, that was solvable for them in a reasonable amount of time. So we want to make sure this model got used, because if we went through all this trouble to solve it in 30 minutes to within 0.5% of optimality, that's great for nerdy engineers like ourselves. But we had to work with the client so that we could automatically take their supplier-based demand and translate it into the right format to read into our model in the 3-digit zip code structure. Because they have their own corporate IT system and their own databases, we basically had to turn apples into oranges. Well, not really oranges. Maybe a Macintosh apple into a Gala apple. In other words, we had to change and massage the data to properly format it to get it into our model. Automatically, we wrote code to do this. We wanted to make sure that the constant information, like the distances and things that don't change on a daily basis, were in one type of file. We kind of left that alone. Another file dynamically did the aggregation of the 3-digit supplier zip codes. And lastly, we wanted to make sure that the distances from the 3-digit zips to each distribution center were managed in a third file. The reason here is, if you have separate input components, and some of them never change, they're static, but others change with each scenario, we wanted to make sure we only had to generate the stuff that changes separately, and we can leave alone the static pieces. We'll verify them occasionally, but once we have them, we've got the distances from A to B. It's not changing because they're not moving. So by taking this data that looked like this to the suppliers and chunking it down and partitioning it and automating the process of writing the code to build the data files, we were promoting them wanting to use our approach, which is important, because if we develop all of this great IE stuff and it never gets used, what have you really done? So we coded up something that automatically took data from their corporate systems, pulled it in, formatted it, wrote the ample data files, automatically generated each test case for us. Because as you'll see in the next lecture, when we start running model scenarios that take 30 minutes each, you don't want to spend 30 minutes running the model and then 4 hours getting the data file for the next model together. So with this code, we could rapidly generate a variety of scenarios, put them on the computers to run overnight, over the weekend, so that every 30 minutes we're getting an answer. And as you'll see in the next lecture with the results, there's a lot of analysis we needed to do once we built all these models. And so to improve the usability, we did a little work on the front end, building a little decision support tool, if you will, to package the data, put it together, generate the data automatically such that we were spending our time analyzing results, not building data files and then hoping they ran well. Plus, by coding this, we were able to kind of guarantee it was all being done consistently and systematically. There was no, oh, I typed in the wrong numbers so the data is invalid, because we were pulling it from the same sources and using the same approaches and methods to build our data files each time. So with that, I bid you good day. Look forward to the next lecture where we're actually going to be talking about, now that we've built this model, we have the data file, what were we able to do with it?